Hello, I'm the Mosaic Mr. Daycock, and today I'm going to be teaching you about differentiating trigonometric functions other than sine and cosine. So on the left here we have a list of all of our other trigonometric functions. So we had sine and cosine, but we've also got tan, secant, cotangent and cosecant, often just referred to as tan, sec, cot and cosec. And here we also have a list of their derivatives. So if f of x is this, then they differentiate to this. So tan of x differentiates to sec squared of x. Cot of x differentiates to negative cosec squared x. And that is really useful. And most of the time you will be just given these formulas in whatever exam you're doing, or if you're doing work, you'll be able to just look them up on the internet, etc. I took this example from the Edexcel formula booklet for A-level, so thank you to Edexcel for that. And generally speaking, you don't need to memorize these at all. Okay, but what I am going to do is I'm going to show you an example of how to use them and the proofs that these are true, the proof that they work. Okay, so let us consider an example. So let's say we had y equals x squared cot of 7x. What is dy by dx? Well, what we're going to do is we're going to say we're going to use our product rule. It's two things multiplied together. So we'd say u equals x squared, v equals cot of 7x. Therefore, u dash is equal to 2x, and v dash is equal to negative, well, our k must be our 7, so negative 7, and of course this isn't surprising, the constant inside comes out, we should be expecting that. Kind of looks like cost there, let me rewrite that. Negative 7 cosec squared of 7x. And therefore, dy by dx must just be equal to x squared multiplied by negative 7 cosec squared of 7x plus 2x multiplied by cot of 7x. And I wrote cost again there. Cot of 7x. And then we can just simplify and we'll get 2x cot 7x minus, because of course of this negative here, x squared cosec squared 7x. And I forgot the 7 in that one, so negative 7x squared cosec squared of 7x. And there you go, that's how you use it. And notice here, all I did was I looked up this bit in the formula based upon my table. Just looked it up in the table. I didn't need to memorize it. I didn't need to know it off by heart. I just looked it up. Nice and easy. But we're mathematicians and we should not just take anything for granted. So what I'm going to do is I'm going to show you the proofs of these. So if y equals tan kx, how can we differentiate that? Well, what we're going to do is we're going to write it as y equals sine of kx over cosine of kx. And we're going to differentiate those using the quotient rule. So we've got u equals sine of kx. U dash, therefore, is cosine of kx, except we need to remember there's a k in front. V is going to be equal to cosine of kx, and v dash is going to be equal to negative sine of kx, except again remembering that that k must come out. And then we just apply our quotient rule. So, quotient rule is dy by dx is going to be equal to u dash v minus uv dash all over v squared. We're just going to plug those in. So we're going to get u dash is k cosine kx. V is just cosine of kx. We're going to subtract u is sine of kx. And v dash is multiplied by negative v dash, negative k sine of kx. All over v squared is going to be cosine kx squared. Now let's simplify it. Here we've got cosine times cosine, so that's going to become k cosine squared of kx. Here we've got sine multiplied by sine and a negative multiplied by negative, so we're going to get plus k sine squared kx. And we can write the denominator as cosine squared of kx. And now, just let's factorize that numerator. So we're going to get k, because we've got k in both of them, cosine squared kx plus sine squared kx. But you should recognize this, and this is something you probably would be expected to remember. Cosine squared plus sine squared is always 1. And so this is equal to k multiplied by 1 all over cosine squared kx, which is just k over cosine squared of kx, or we could write that as k multiplied by 1 over, that looks like a plus, 1 over cosine squared of kx, and 1 over cosine, that is our sec. And so this is equal to k sec squared of kx, as required. So there's a proof that if we start with y equals tan of kx, we'll get k is the sec squared of kx. And we'll just use the quotient rule for that. So next one, let's do sec. Sec differentiates to k sec kx tan kx. Let's prove that one. Now this one here, let's imagine we've got y equals sec of x. And as always, just like we did last time, we want to write it in terms of sine and cosine because we know what's going on with those. So I'm going to write this as actually y equals 1 over cosine of x. And 1 over cosine of x, well, we've got y is equal to cosine of x all to the power of -1, and so I'm going to use the chain rule. You could also use the quotient rule, but let's use the chain rule here. So I'm going to say u equals cosine of x, and y therefore equals u to the -1. And this will give me that du by dx is equal to negative sine of x, and it will give me that dy by du is equal to negative u to the -2. And therefore, dy by dx is going to be equal to negative u to the -2 multiplied by negative sine of u. Oh, sorry, that's x there, obviously. Which will give us, and let's simplify that, so we're going to get the negatives are going to multiply to positive, and u to the -2 is, we're going to get sine of x over u squared. And now we know that but remember we know that u was cosine x, so that's going to give us sine x over cosine squared of x. If we want to separate that slightly, we're going to write that as sine of x over cosine of x multiplied by 1 over cosine of x. All I did there was I took this cosine squared and split it into cosine times cosine. And now we know what these are. Sine x over cosine x is tan x, and 1 over cosine x is sec x. Except throughout all of that, I forgot to write the k, so let's re-add that back in. So here this is sec kx, here's 1 over cosine kx, there's another x, here's an x, And therefore, at this point, we're going to get an x in here, sorry, a k, and we're going to get a k there. So that k has come out in this sign. Everywhere else there's no extra k. So here we get an extra k, special k, and obviously we've also got the k in here. So we've got a k here and out here, which means we've still got a k out here the whole time and in here. And of course, there must be a k in there. K, k, we've got another k here, and that lastly gives us, that lastly will give us k tan kx sec kx. And there you go. So that is as required. This time remembering the k's have to be there as well. Cot of kx, let's see what happens there. So if we've got cot, got y equals cot of kx, well that's the same as y equals 1 over tan, and therefore it's y equals cosine of kx over sine of kx. And in this way, our quotient rule is going to work out in a very, very similar way. If you want to, you can go through this one yourself, but it's going to we're going to end up with something like k multiplied by minus cosine squared of kx minus sine squared of kx all over sine of kx squared, and that is definitely not an equal sign. That's dy by dx equals. And then we would factor out this negative, and you can see this for yourself if you think about the quotient rule, the way it works. Because we've got the fraction the other way up, everything sort of ends up the other way around, and so we end up with negative k times by 1 all over sine squared kx, which is negative k cosec squared kx as required. And lastly, cosec differentiates to minus cosec kx cot kx, and again it's going to be very similar to the other one, and as you can see, you can probably see the symmetry in the formula. If we have y equals cosec kx, well then I'm going to write this as y equals sine of kx all to the power of negative 1. And so I'm going to have u equals sine of kx, that y equals u to the minus 1, and that's going to give me du by dx, let's be consistent, of k cosine kx. And here we're going to get dy by du is equal to minus u to the minus 2, and therefore dy by dx is equal to minus u to the minus 2 times by k cosine kx, which is going to give us negative in front. The negative won't disappear here, which is why we're left with, won't cancel out because we aren't left with which is why we are left with a negative in this one, all over u squared. U squared is of course sine, so we're going to end up with minus k cosine of kx all over sine squared of kx. And then, just as before, I split that into minus k cosine of kx over sine of kx multiplied by 1 over sine kx, which gives us it's minus k cot of kx multiplied by cosec squared, oh no, not squared, just cosec of kx. Okay, and I went through those last two fairly quickly because they are very, very similar to the first two. If you want to be absolutely certain of how to do the second two, I recommend practicing it yourself or pausing the video and going through a bit more slowly. But ultimately, the principle is the same. All you want to do in every case is rewrite this or this or this in terms of sine and cosine. So here it is sine kx over cosine kx, and here it's just 1 over cosine kx. Here it is cosine kx over sine kx, and lastly we have 1 over sine kx. You rewrite them as what they are in terms of sine and cosine, and then differentiate using the sine rule or differentiate using quotient rule or chain rule. The quotient rule will work for everyone. The chain rule only really works for these two, but it's up to you either way. Okay, thank you very much for watching, and I'll see you in the next video.